Okay, so we're happy to have Lorenzo Gagliotti from uh, Amsterdam University College, University of Amsterdam, talking about order types of models of arithmetic without induction. And Benedict Lowe, his co-author, is here as well. So we're happy to have you both. Go ahead.
Okay, so thank you first of all for inviting me to give this talk. So yes, as you said, I will talk about order types of models of arithmetics without induction, so fragments of arithmetics. This is actually a quite old project that I did with Benedict. So I did this as a side project in my first year, I think, of PhD, so a long time ago. And I see that in the audience there are many experts in models of PA, so I hope I won't disappoint you. So I won't prove anything big. This is just going to be a collection of results that we have on these syntactic fragments of PA, essentially. So let me start from the beginning. So we all know that given by compactness or in completeness theorem, there are no standard models of PA. So these are models that are not isomorphic to the standard model of natural numbers with the classical operations. And in this talk, we will be talking about order types. So the one thing you have to note is that actually you can split every model of PA using Archimedean classes. So this would be just taking each point and look at elements that are at finite distance from that point. So this splits your linear order, and it splits it in this way, as I mentioned here. Can you all see my yeah?
Yes.
Okay. Yeah, so this also, let me tell you my notation. So this is just saying that every model of PA will start with a copy of N, followed by D copies of Z, whatever D is. And for PA, we know that D has to be at least dense linear order without endpoints. And so this immediately gives you that in the countable case, we exactly know what the order type is going to be, right? So because there is only one such D in the countable case. So so for countable non-standard models, we know that they all look like N times Q copies of Z. And of course, now the natural question is to ask what this D can be, right? And this is far from solved. So this is actually a very complex question. I'm sure that many of you already know that there are many studies on this and many results on what can and cannot be what this D can or cannot be. Connected to this field, so this question is also this question by Friedman, which asks whether there are two consistent extensions of PA, T and T prime, that can be distinguished using order types. So by these, we mean that the class of order types of models of T and the class of order types of model of T prime are different. And this question is also widely open, quite complex. There are also several versions of this question, and they are all still open. And today I will really look at something that is much simpler than all of this. So I will be inspired essentially by a downward version of this question, which then, so if you just rephrase what I just said downward, you get this question here that says, well, are there two fragments of Peano arithmetic, T and T prime, which can be distinguished using their order types? So this is what inspires our question, our talk today. So what I would do is essentially look at, well, I would say meaningful, some meaningful fragment of PA and their order type, and show that they can actually all be distinguished using order types. And as I said, as the title says, we will focus particularly on fragments without induction, and I will tell you in a moment. Well, you can already imagine why I'm doing that, because it's much simpler. But I will explain it a bit better in a moment. So before we start, we have to fix a few things. In particular, we have to fix what PA is. So usually you don't really care about which version of the axioms and of the language, even of PA, you are talking about, because things are usually provable or interdefinable. So it doesn't really matter which language and which axioms you are actually talking about. But for us, since we are really working on syntactic fragments of PA, we have to fix a language, and we want that to be essentially as rich as possible. And we also will have to fix our axioms. And I will discuss this in a moment. So for me, the language of PA is the language with zero order relation, successor function, plus and times. And I will be looking at two sub-languages of this language, namely the language with only order and successor. This will give us successor arithmetic, and the language with successor and plus, and this will give us order, successor, and plus, and this will give us Pressburger arithmetic, so the additive fragment of PA. And I will also look at versions of this with and without induction, and I will use a minus for those theories which do not have induction. So essentially, this gives us 6 theories, including PA and PA minus. And some of you can already maybe wonder why I'm not looking at the multiplicative fragment. And so there are essentially 2 reasons. So if we just really look at the language where you only have multiplication, well, then you don't have an order there. And if you look at the language where you have both order and multiplication, well, then you can actually show that you can define addition. So this is why I'm not looking at what is called column arithmetic here in this context. Okay, so this is about the language. Let me also fix the axioms. I hope this is not gonna bore you too much. So as I said, we have to be careful because sometimes people tend to remove axioms because they can be proved from the others. And since we are going to look at fragments, we have to be precise with what we mean. So let me just quickly go through them and maybe say something about these axioms. So we have 4 axioms for the order. This just say the usual thing that the order is a total order with a minimum without a maximum. Then we have the axiom for successor function that, well, tell you that successor function is a monotone function and that everything but 0 as a successor. And then we have the axioms for plus. Again, nothing special about this. The next one is usually an axiom. So with this star axiom is usually something that is not included in PA. So this is just, this tells you that difference exists, right? So if you take x smaller than y, then you also have y minus x in your model. So this is usually not included because it can be proved using induction. But actually, if you want to get Pressburger arithmetic, when you restrict yourself to the language with only plus and the order, then you actually need to include this axiom here. And then we have the axioms for multiplication. Again, nothing really special. And the induction schema. So one thing that maybe it's worth noticing here is that if you look at the axioms without induction schema, then they are all universal with the exception of this star axiom here and this S1 here. And this is essentially, as I will tell you in a moment, one of the reasons why we look at fragments without induction, because in this case, when you have this, your axioms are universal, essentially your model really behave more like algebraic structures. Okay, so these are the 6 theories we are gonna talk about. I already told you what they are. So SA is successor arithmetic, PR is Pressburger, and PA is PA. Okay. So let's get back to our question. Now, the question we are going to look at is whether we can distinguish these theories using order types. So for every pair of theories, we want to find an order type which appears as an order type of a non-standard model of one theory, but not of the other, right? And we immediately have that because of containment, some arrows, some directions are not allowed, right? So in particular, if something is a model of SA, this is also a model of SA minus. So this also means that every order type of SA is going to be an order type of SA minus. And the same with the other containment. So what I'm going to look at is actually this graph, where an arrow from A to B means that every order type of A is an order type of B. So these arrows are just those that I got from the containment relation. Okay, so now what we want to do is to study these 6 theories. But before we even start, let me talk about the special case, which is successor arithmetic. So successor arithmetic is actually a very well-known theory. So this is just the theory of discrete linear order with an strictly increasing successor function. And actually, it is an exercise essentially to show that this theory has quantifier elimination. And this in turn tells you that the theory SA minus can actually prove the induction schema. So this also tells you that SA and SA minus are actually just axiomatizing the same theory. So in turn, this simplifies our work because it means that our graph is actually house-shaped and not a rectangle as it was before. So this is the actual starting point we have. And essentially, we now want to look at all the reverse of these arrows, whether they can happen or not. Okay, so before I go on, let me talk to you about why we are looking at, we are particularly interested in theories without induction. And so, as I said before, the idea is that if you look at the set of axioms we selected, essentially all of them are universal except for these 2 axioms, the star axiom and the one saying that every number as a predecessor. And actually, so if you look at this, essentially they, for this reason, essentially models of these theories really look like algebraic.
Lorenzo, can I ask something at this point?
Yeah.
Because you went over the axioms quickly, so you saw so the induction schema includes the induction schema with parameters. Have you considered these theories when you have induction schema without parameters?
No. So that of course you can also look at portions of induction schema and other version, but we didn't look at that. So that's actually a natural direction after this project would be to look at fragments of induction, for example.
But I mean, but there's this curious thing that, so there are those I sigma n and all of when you do fragments of induction. But this whole thing that there has been some interesting work at some point of K, Dimitrokopoulos and Saman Paris, and what happens when you do not allow parameters but still keep strong fragments of induction. For PA, it doesn't matter because it's equivalent. But it would be, and I don't know, I haven't even thought about it, how it would affect those weaker theories.
Yeah. So I don't know
anyway,
if that's thought about this. We didn't.
All right. Thank you.
Okay. So as I was saying, so this is a bit of a digression that I want to take to just look at this non-standard models, and the idea is that we just try to build some of these models and see that it really always like closing under like you can get this model by closing under operations essentially. So in particular, for example, if I want to look at non-standard models of SA, say, right? So the first thing I have to note is that all this business with Archimedean classes is gonna work exactly the same for SA. So you don't really need the operations, you just need successor function. So that your model is still gonna look like something like n plus z times d for some linear order d. And so if you want to build a non-standard model of this, of SA, for example, you would start with a copy of natural numbers. And then the simplest thing you can do is actually add a non-standard point, right? And then if you look at the axioms, what they are saying is just really that every point should have a successor and every point but 0 should have a predecessor. So you can just close, so to get a model of SA, you can just close these under successor and under predecessor function. So you get a copy of Z here. And this is actually a model of SA. And it's sort of a minimal non-standard model of SA. So this is what you get. And of course, if now I want to change this into a model of PR minus, what I need to do is just close under addition, essentially. And of course, adding a standard and a non-standard point, well, it still gets me into this bubble here, right? So if I want to do A plus N, this gets me into the bubble. But of course, I have to, you also have to add A to itself, and you can do this as much as you want, right? As you want, right? So you get A plus A, which is a new non-standard point, which has to be bigger than all of these points in this bubble, right? And again, you have to close under predecessor and successor, so you will get something, a new bubble. And of course, you can go on like this, right? So if you keep doing this, you get this nicer picture than that I just drew, right? So this is and this is a model. You can see that this is a model of PR. So this is again telling you that if you don't look at induction, you can easily get non-standard models of these theories by just closing under the operations. One thing is that this is actually a bit of a special case. So that this model with one generator is actually a bit of a special case. And indeed, if you try to do things a bit more complicated, so for example, if you, instead of starting with one generator, you start with two, so you start with a copy of the natural numbers and then two non-standard points. Well, for SA, that's easy to make this into a model of SA, because you can just close each of these under successor and under predecessor. So you will get two copies of Z here. So this gives you a model of SA. But for PR, things are a bit more complicated. So if you start doing what we did before, what you would do is now, well, start adding everything. So if you add A or B with a standard number, that's not a problem. But if you add A with itself, then you will have to add all of this Archimedean classes that we added before, and you have to do the same with B. But also you have to look at those Archimedean classes that are of the form A plus B, for example, right? So if you do that, you get something that looks like that. So each one of these is n times a copy of Z. And it looks like this should be a model of PR, but it's actually not. And this is just because of this star axiom. So the star axiom also tells you that there must be differences. And so this doesn't have that. So what you have to do is also look at all of the things of the form B minus A, B minus 2A, and so on, right? So, and if you, but still you can essentially just close what we just saw under this operation. This is preventing you from seeing. So if you do that, right, so this star axiom is not universal, but it's still defining a function essentially. So what you can do is close under that function, and you will get a model of PR. And actually, you get a model of that order type there. So n plus a copy, n times n copies of Z, followed by n copy of Z squared. So this is the same order type as a polynomial of degree at most 2, essentially. Okay, so this is just to give you this idea that if you don't look, so if you have theories without induction, there is a very concrete way of building these models, and this is something that will come out also in the very first last part of this talk. Okay, So let's look at the graph now. I also hope that I convince you enough that you can build models of SA starting from any linear order you like, right? Just by doing what we just did. So you have a linear order which will act as the generators of your non-standard model, and then you close under successor and predecessor, and this will give you a model of SA.
Lorenzo, I'm a bit confused because now with SA there is no ordering.
It is ordered because we have so SA for us is order plus successor.
Oh, I see. So sorry. I thought it was this. So I thought it was just successor.
No. It's order plus successor.
Sorry, I forgot.
Okay. Okay. Where was here? Yeah. So So what I just did, I hope convince you that if you take some linear order A, you can use that to generate a model of successor arithmetic. And this also tells you immediately that you can immediately see that, for example, there is no model of PR minus of order type n plus z, right? Because that cannot be closed under adding the non-standard point in this Z Archimedean class, in this non-standard Archimedean class, which is on top of n. So this immediately tells you that, well, these two arrows are not possible, right? Okay, so this was easy. So what we want to do now is to focus on these four guys underneath. And the first thing I want to look at is Pressburger arithmetic. And actually for PR, we are in a very nice position because there is actually a full characterization of models of PR and PR minus. Modulo, well, the fact that we don't actually know what the order type of divisible abelian groups look like. So if you that's the missing information. So this is essentially something that is a reformulation of something that was in Lowell-John's PhD thesis. So I don't think that the result was there as it is, but the idea was there. And this result gives you a full characterization of models of PR minus and PR. So it tells you that a model of PR minus should look like something that I call the standard monoid over an abelian group. So what is this? Well, it's something that, well, looks like this. So the order type is the one given here. So it's just n plus z times the positive part of your group. And all the operations are actually defined pointwise. So you can look at these points, of course, as pairs z and one point in the group, right? And do addition pointwise and order anti-lexicographic and so on, right? So you can, so you define everything in the obvious way, and you get that this is actually isomorphic to your model. So in particular, this gives us again, modulo the fact that we don't know how abelian group look like, gives you a characterization of order types of models of PR minus. And for PR, what you need to add is just the visibility of the group. And this may sound obvious, I guess, to you if you have looked at PA, for example, and the fact that the induction schema essentially forces you to have a dense linear order for the Archimedean classes. So this is essentially a very, very similar thing. Okay, so this is a nice result. So we have full information and immediately gives us some way of distinguishing PA from PR and PA minus from PR minus. And this is because of a very well-known result from Potov. So it is well known that that R cannot be one of these dense linear orders that comes in as an order type of non-standard model of PA. And actually, the result from Potov can be proved also without using induction. So this is not very hard to see. So the standard proof, one of the standard proofs actually does work in PA minus. So this in particular tells us that there is no model of PA minus of order type n plus z times r. But of course, the result that we have just seen tells us that there is a model of PR which is of that type, right? Because, well, you just need to have that R is the order type of a positive divisible abelian group. Well, but R is a field, so in particular is a positive divisible, it is a divisible group, and the positive part of R, of course, has the same order type of R itself. So this gives us the fact that PR, there is a model of PR of this order type. And so this in particular allows us to draw these two arrows here, right? So there is a model of PR which is not a model of PA, and of course, since every model of PR is a model of PR minus, there is also a model of PR minus which is not a model of PA minus. So what we are interested in now is only these two arrows here. But before we actually look at that, I want to look back at the characterization of models of PR minus that we had, and actually to refine it a bit. And you can do that essentially using a result that is in Rosenstein. So this tells you how groupable linear order look like. So groupable here means that you can that there is a abelian order group which has exactly that order type. So how do they look like? Well, they look like something of this form. I don't want this. I want this. Something of this form. So z to the alpha, where alpha is an ordinal, times the order type of an densely ordered abelian group. So again, we kind of have the characterization modulo some order type of groups that we don't really know that much about. So if you put this together with what we had before, so now we have that a model of PR minus must look like something like this. So n plus z times z to the alpha times d plus, where, well, alpha is an ordinal and d is a densely ordered abelian group. And of course, plus just means the positive part of that. And actually, this is quite nice because it tells you two things. That the model we built up when we were just like building a model of PR minus using one generator is somehow the minimal model for this, because it's the one you get where D is the 1 point or abelian group, and alpha is 1. So that's the minimal. It's sort of the minimal thing you can, the minimal no standard order type you can get, and also that the one that we did with the one that we build with two generators is the sort of successor of that, because you can build that, because that's exactly the order type you get with alpha equal to 2, and D again being the 1 point abelian group.
Excuse me, maybe I should, or maybe I missed it, but I don't think I know what you mean by order type Z to the alpha.
So this is the order type of all the functions from alpha to Z with finite support. Is it exactly like in the ordinals?
Okay. And then you just take the order product. All right. Oh, I see. It's just like I would talk about omega to the alpha, but it's Z to the alpha.
Yeah, exactly.
Okay.
And and on ordinals, they are just the ordinal exponentiation. Yeah. Okay, so we gave slightly finer characterization. As far as I know, not much is known about the order type of abelian groups, densely ordered abelian groups. I tried to find a bit more information about this, but I'm not sure this is actually well studied. If any of you actually has some source for this, I would be happy to, because this is really bothering me, and Benedict knows this. So if any of you know something about it, please let me know. Okay, so we are now again back to the graph, and we now look at these two arrows here. And before we go on with that, so I'm now gonna introduce a machinery which is actually not needed at all to prove that these two arrows cannot be reversed. So you can actually just show that there are two models distinguishing this, but I will actually show that using much more general machinery by essentially formal power series. And this is just because I want to show you that, again, given this idea that models of PR minus and PA minus can be built with this really like concretely built, you can actually build many of these models. So this is what I'm gonna do now. So introduce essentially a way of building many models of PR minus and PA minus. And the idea is that, again, look at what we did before, right? So the first model that we built of PR minus was, well, if you look at that, that was just the model, a model that looks like monomials, essentially, over Z. And the second model, I told you, well, this is just polynomials of degree 2 over Z. So the idea is to essentially generalize that. So the idea is we generalize the notion of polynomials over a ring and use that to generate many models of PR minus and PA minus. So this is using formal power series. So you can really think about them as formal sums, where, well, this function FA just gives you the a coefficient at each exponent, right? So formally, what we will look at is, so to do that, what you need is essentially a set of exponents, so a linear order, and this will be the exponents of our polynomial, and a base, which will just be the coefficients of the polynomial. And then we look at functions that go from, well, exponents to B union Z. This is a bit, it seems artificial, but it's just really because we would like this to, we want to have that the coefficient of the polynomial of degree 0 should be integers, right? Because we want, again, eventually we want to get a model of PR. So that's the only reason for that. And so then we look at functions of this type, which are like that. So their support is reverse well-founded. So this is just is just because in this way you have a leading term. And then you also want to just look at positive polynomials. So the leading term should not be negative. And again, as I said before, we want the coefficient of the polynomial to be in Z, the coefficient of degree 0. So we look at all of these functions, and these is what I will call positive formal power series with base B and exponent gamma. Okay, so the idea is now to use this to produce models of PR minus. And indeed, if you're indeed to do that, what you need to do is to just add some structure to this set of functions, right? So far I only told you that we have this set of functions, but of course you can define order, successor, and plus, just as you would with polynomials, right? So the order is anti-lexicographic. Successor is just adding 1 to the zero coefficient, to the coefficient at 0, and plus is just pointwise plus. And if you do that, well, then you end up, this is just an exercise, you end up with a model of PR minus. And we get, from that, we actually get back the model we built before. So these monomials, right? So you can instantiate these with 2 as your exponent and Z as your base. And what you get is exactly the models we have seen, the model we have seen before. And as I said before, when we were looking at characterizations of PR minus, actually, this is a minimal model for PR. And one can actually prove it. So we can prove that this essentially works like a prime model for non-standard models of PR. So if you take a non-standard model of PR, there is an isomorphic copy of the monomials in that model. And you can actually use this to prove something also, which I think is nice, namely that any non-standard model of PR minus as a proper non-standard submodel. And how you do that? Well, because of this theorem that we have here, right? So every model will have a copy of the monomials. We only need to care about monomials, of course. And then, well, to get a proper submodel of the model of monomials, you can just look at those monomials of which have even coefficients. So you just need to check that this is closed under addition, and it is. And so this gives you a proper submodel of PR minus in your model. Okay, so this is for PR minus. Actually, maybe I also say this. You can actually extend this to actually produce models of PR. And in that case, here you would need a divisible ordered abelian group. And then in that case, you actually get full PR, which is not surprising given what we saw before. Okay, so immediately this gives us a way of distinguishing between PR and PR minus, right? Because now we have this model of monomials. Well, we could do this before, as I said, right? So we have this model of monomials, which cannot be a model of PR because of the characterization we had before from Lowery-Jones, right? So this immediately gives us that this arrow cannot be, yeah? Okay, so now we only need to distinguish PA minus from PA, and we are done. And again, I will use this way too general way of doing this, which is use formal power series again. So you can actually extend formal power series to allow for multiplication. And well, you just have to do the same thing you do with polynomials. Right, so you just want to do polynomial multiplication, and this also means that you need a bit more structure for your exponent, right? You need to be able to do addition, and of course you need to be able to do multiplication of coefficients. But so if you have that and then define multiplication as you would with polynomials, then you get a model of PA minus. So these again can be used to generate many of these models. And again, we get polynomials, like standard polynomials on Z, back from this by instantiating the base to be Z and gamma to be the natural numbers. So in particular, again, this gives us a model which is minimal for PA minus. So again, using the same technique, you can prove that every non-standard model of PA minus actually must contain an isomorphic copy of this. So this is just really by taking a generator and closing under the operations again. So you just get an isomorphic copy of that. And again, using a similar thing that we did before, you can prove that every non-standard model of PA has a proper non-standard submodel. And in this case, what you have to do is, again, look at the polynomials and look at polynomials with even degree. And this will give you the models of PA minus, the submodel of PA minus that you're looking for. Okay, so this again allows us to actually draw this arrow, right? Because of course, the model of polynomials cannot be a model of PA minus. So this ends our work on this graph. So it tells us that this is actually a complete graph, and we cannot, there is no arrow that is reversible. As I said, you could have proven this with way easier proofs by just giving these models that I showed, right? So these monomials, these polynomials, and using those. Now I want to show you why I presented the machinery of this formal power series. And this is essentially because, as I said, this allows you to build up in a very concrete way many models of PA minus. And this gives you a way of generalizing, not generalizing, but I don't even know, it's not refining, but so of proving a version of this result from Shelah. So this is a very general theorem that Shelah proved in proving this non-structure theorem. And it's really very general. So it's a model theoretic theorem saying that, well, you take your favorite lambda uncountable cardinal, regular cardinal, and you take two languages. One should be an extension of the other, right? And then you take two theories, and one should be in the extended language and one should be in the base language, and the one in the extended language should extend the smaller theory. Then if your big theory has an infinite model and your small theory actually is non-stable, then you have maximally many non-isomorphic model of the small theory of size lambda, which are actually reducts of models of the big theory. So why does this why is this important for us? Because, well, it shows in particular that there are maximally many models of PA minus of size lambda for any uncountable regular cardinal. So in particular, if you instantiate this theorem with discrete linear order, so this is kind of the basic, so the standard example of non-stable theory, and you take T prime to be, so the larger theory to be PA minus, then you get exactly that. There are two to the lambda many, so maximally many order types of models of PA minus of size lambda. So there are two things here. So first of all, that lambda has to be an uncountable regular cardinal. So it cannot be omega in particular. And second thing, we have no, so this is a very general result, and it gives you no information about these models that you get. So the idea would be to actually kind of use formal power series to actually prove a similar result, but in a much more concrete way. So let's try to do this. So of course, if the idea would be to actually use ordinals as your exponents for your formal polynomials. And so the first thing you have to be sure about is that if you take two different ordinals and you look at formal power series generated with those ordinals, you actually do get to non-isomorphic, to models that are not order isomorphic, right? And actually, this is indeed the case. So if you take two different ordinals, you actually get two models of two set of formal power series which are not order isomorphic. This is actually not completely trivial to prove. So the way in which we prove it is essentially showing that if beta is bigger than alpha, then the ordinal omega to beta is embeddable in the formal power series generated by beta, but not in that generated by alpha. So we have that, but of course, this doesn't tell us that we can generate models of PA at all, because we had these conditions on the exponents. So the first thing we have to make sure is that we keep the ordinals with the right structure, and that the thing we get is actually of the models we get are actually of the right size. And of course, if you just use ordinals with standard operations, you don't get an ordered abelian monoid. Particularly, you know that addition is not commutative at all for ordinals, but there is a quite standard solution to this, which is to use natural operations, sometimes called also Hessenberg operations. So this is a commutative version of addition and, well, multiplication for over the ordinals. And essentially you get this by looking at counternormal form of ordinals and adding them as if they were polynomials over omega. Okay, so we can use those operations. And of course, we need to be sure that the ordinals we use are closed under this addition. And well, fortunately enough, being closed under natural addition is the same as being closed under classical addition, ordinal addition. So we have a full characterization of that. So those are exactly those ordinals of the type omega to the alpha for some ordinal alpha. So now we just really need to put things together. So the one thing you have to note is that if you look at ordinals in between lambda and lambda plus, right? Well, there are lambda plus many ordinals of the type omega to the alpha in between lambda and lambda plus. And then they are, of course, all of size lambda. And the second thing you have to note is that if you generate your formal power series with these ordinals, well, you are looking at so formal power series with ordinals will just be really finite polynomials with ordinal exponents. So these will all be of size lambda. So if you put all of the things together and you use the results we had before, so we get that there are at least lambda plus many non-isomorphic ordered types of models of PA minus of cardinality lambda. So this is somehow different from what you get from Shelah, right? So here, lambda can be any regular cardinal, and so also it can also be omega, but we don't get maximality directly, but we get lambda plus. So you will need CH to actually prove GCH to actually prove maximality. Another thing that you get because of the way in which we build all of these models is that all of these models will be models of PA minus of cardinality lambda, but they will not be ordered types of models of PR or PA. So this really tells you that you can build lambda plus many ordered types, which are ordered types of PA minus, models that are ordered types of PA minus, but not of PR and PA. So it gives you this additional information. Okay, so this is really the last result I wanted to show. Let me just end by giving you a recap of what we did, which may have been a bit fast. So the idea was really to look at some meaningful subtheories of PA. So these are the 6 subtheories that we looked at, and we actually proved that you can use order types to distinguish all of them. So this is actually something that is not that complicated, but along the way we proved several properties of these theories. In particular, we gave a full characterization of PR minus and of models of PR minus and PR, and we proved some properties of non-standard models, so minimal non-standard models of this theory of PR minus and PA minus, for example. And we also look at a way of generating many models of PR minus and PA minus using this formal power series, which again, I mean, it's really like the nice thing of these models is that they are really concrete. It really gives you this idea that you can really concretely build this model and you have full control on them in some sense. And we use that to prove a version of a result from Shelah and to extend it to omega and under CH to actually prove a slightly better result. So thank you for listening to me, and I'm here for questions.
Okay, thank you, Lorenzo. I am opening up for questions from anyone, so feel free to unmute yourself and go ahead. Okay, I'll start. I guess you mentioned this earlier on, that essentially you didn't look at any fragments of induction or anything like that, but I think there's something. Yeah, I mean, so if we look at these sort of formal power series models, essentially you can only do this with the algebraic structure, right? So if you add even the smallest amount, if you start at delta zero, can you get
Well, I mean, like you get something, right? Because
It's
so
something.
for PR, if you start with a divisible group as your base, then you get a model of PR, a full PR. It's with PA that is not clear.
Right. Okay. Okay.
But then, yeah, yeah. So it's not completely. But yeah, I'm actually also interested in fragments of especially open induction. I would be.
If I may add, I think in the case of PR, this is just a strange feature of Pressburger's theorem, right? Because essentially Pressburger's theorem tells you that it is only divisibility that matters, and then you get all of induction, which is weird because you somehow encapsulate all of induction essentially in these almost trivial looking axioms. That's why it works in the case of PR.
Right. Thank you.
So I have a short question that again I haven't really thought about at all. But so for PA, what matters for the redux is the Tenenbaum phenomenon. And now, when you have those representations for models of PR in this algebraic way, can you recognize which of them are recursively saturated? Which means which are expandable to models of PA.
So which of these are recursive and expandable to a model of PA?
No, that's equivalent actually. To be expandable to a model of PA and countable, you have to be recursively saturated.
Yeah.
So can you recognize them from the representations?
We didn't really look at this. This is actually a very interesting question. But yeah, no, we didn't really look at this.
Yeah, because one thing that recursive saturation implies already that you must have rich automorphism groups and other kinds of properties that they're usually quite unique among other non-recursively saturated. So maybe this is some sort of easy way of seeing that in those components that you have those divisible abelian groups or whatever you use in the.
Yeah, maybe if the group, the divisible abelian group was recursively saturated, then.
Yeah. Okay. Yeah, Benedict, do you have any?
No, I have no intelligent thing to say about this.
Okay. Any other questions?
Well, I don't know if Alf is still there, but for Benedict and Lorenzo, Alf had a comment about the other types of divisible abelian groups somewhere in the chat.
I'll say that I had some vague recollection, which is probably wrong, that for divisible order abelian groups, the underlying orders, it's obvious that the underlying orders have to be doubly transitive. And I think that's close to being enough, but I don't remember the details anymore. And I may be completely wrong, but I have some vague recollection this is the case.
You don't remember where you got this, or?
No. I just have some very vague idea that doubly transitive is an important part of it, but how exactly that works, I don't remember anymore.
I mean, of course, a follow-up question would be: do we I mean, even if this is equivalent, do we have any better characterization of the doubly transitive dense linear orders?
Oh, yeah, who knows?
Because this may just be replacing one thing with another, of which we also don't really know what it looks like.
In some sense, doubly transitive is much more concrete property.
The point is, you can axiotize double transitivity, sort of. So, I mean, that's one of the reasons, right, that the doubly transitive orders do form a PC class, which is a nice thing to know. And simple has a simple activization and that kind of stuff, and you can first order exercise them, sort of. But yeah, I don't remember the details anymore. I may be completely wrong too.
Thank you.
Okay. Other questions or comments or anything? Okay. Let's thank Lorenzo again. That was a very nice talk. Thank you.
Thank you, Lorenzo. It's good.
Thank you for inviting us.